Welcome to This Explainer. Today, we're embarking on what's honestly an epic, almost unbelievable journey. We're going to track the life of an ordinary-looking rock as it's pulled right out of the earth and then subjected to an absolute gauntlet of extreme chemical and electrical trials. The final destination? It becomes one of the most ubiquitous, essential metals on our entire planet, aluminum. From the wings of the airplanes we fly in to the antiperspirants we literally use every single morning, this metal is just everywhere. But getting it out of the dirt? Well, as you'll see, that is an incredible feat of human ingenuity.
Okay, let's dive into our roadmap for today. We'll start with part 1, the hidden metal, then 2, mining bauxite ore, part 3, the Bayer process, 4, the Hall-Héroult process, and finally, part 5, everyday aluminum applications. All right, part 1, the hidden metal. Let's look at a bit of the history of aluminum.
To really understand the value of aluminum, we have to look at just how elusive it was throughout history. It's wild to think, but ancient Greeks and Romans actually used aluminum salts as dyeing mordants and astringents for dressing wounds. They just had absolutely no idea the pure metal was locked inside. It wasn't until 1761 that Gaëtan de Morveau suggested calling the base aluminy. Then, fast forward to 1808, and Humphrey Davy identifies the existence of this metal base, calling it aluminium and later aluminium. But hey, identifying it and actually holding it in your hand are two very different things. It took all the way until 1827 for Friedrich Weyler to be credited with fully isolating pure aluminum. Think about that. Centuries of scientific advancement just to pry this ghost-like metal away from the elements it naturally binds to.
Here's the real kicker. Aluminum is literally obsessed with oxygen. And that intense chemical bond is the ultimate problem that industrial chemistry had to solve. Unlike gold or silver, you can't just stumble upon a shiny nugget of pure aluminum sitting in a riverbed somewhere. No way. Because of its massive affinity for oxygen, it's almost never found in its free elemental state in nature. It is almost always found stubbornly locked up as oxides or silicates.
Moving right along to part 2, mining bauxite ore. This is our source. Take a look at this. This reddish, pebbly dirt is bauxite, the chief aluminum ore. It occurs pretty close to the Earth's surface in seams that can vary anywhere from 1 to 9 meters deep, usually forming as these small, reddish pebbles called pisolites. But, as we just talked about, this mined bauxite is far from pure. It only contains about 30 to 54% pure alumina. The rest of it? It's just a messy, stubborn mixture of silica, various iron oxides, and titanium dioxide. Before we can even think about making metal, we've got to strip all of that junk away. So turning that dirt into shiny metal is basically a two-part boss battle. First, we chemically purify the bauxite into alumina using the Bayer process, and then second, we electrify that alumina to separate the metal from the oxygen using the Hall-Héroult process. Which brings us to part 3, the Bayer process. Time to strip the dirt. We put this crude ore through an absolute wringer of specific phases to transform it. We start by grinding the bauxite down. Then it faces some truly extreme conditions. It gets heated with caustic soda at massive pressures. We're talking over 30 times atmospheric pressure, and at temperatures nearing 600 Kelvin. This dissolves the aluminum components while totally leaving the garbage behind. Eventually, the mixture is cooled down, which allows pure aluminum hydroxide to crystallize right out. And for the final step, it's dried and calcined, meaning it gets blasted with heat at 1273 Kelvin to decompose it into pure alumina and water. Picture this on a real-world industrial scale. You have this raw bauxite being digested in these massive, pressurized vats. The caustic soda acts like a hardcore chemical solvent, selectively dissolving the aluminum right out of the rock, while the intense heat and pressure just accelerate the whole reaction. It then moves through clarification and precipitation tanks, separating that valuable alumina from all the waste. Now, you can't dissolve all that rock without creating a ton of leftover junk. While the aluminum dissolves, the insoluble iron oxides, titanium oxides, and silicic acids settle out, forming this massive waste byproduct that industry insiders call red mud. Once we filter out that red mud and the remaining liquid is crystallized and baked, we are finally left with a fine white powder, purified alumina. But our rock's journey is far from over. The aluminum is pure from the dirt, sure, but it's still stubbornly locked together with those oxygen molecules. All right, part 4, the Hall-Héroult process. This is where we finally rip away the oxygen. So right out of the gate, engineers hit a massive wall here. Pure aluminum oxide has a normal melting point of around 2273 Kelvin. Trying to reach and maintain that kind of crazy heat on an industrial scale is just devastatingly difficult and expensive. Melting pure alumina was practically impossible for a commercial operation. But then, chemists found a real game changer, a clever solvent that drastically lowered the required temperature, dropping the melting point by a massive 1,000 degrees. That magic solvent? It's called cryolite. By dissolving about 13% of the produced alumina in a bath of molten cryolite, and then throwing a bit of aluminum fluoride into the mix, the solution actually becomes an electrically conductive liquid at a much more manageable 1273 Kelvin. This single chemical workaround is literally the secret sauce that makes modern commercial aluminum production physically and economically possible. Okay, now for the fun part. We apply the electricity. Inside these massive carbon-lined electrolysis pots, or crucibles, heavy electrical currents are pumped right through the molten mixture. We are talking hundreds of thousands of amps here. This massive electrical force literally rips the oxygen away from the aluminum. And there's a really beautiful bit of physics that happens next. At 1273 Kelvin, the newly freed pure liquid aluminum is actually denser than the molten cryolite floating above it, so it safely sinks right down to the bottom of the pot, resting on the carbon cathode where it can be tapped and collected. But there's a catch, and it's a big one. Remember all that oxygen we just violently ripped away? Well, it has to go somewhere. It forms at the positive carbon electrodes up top. And at these extreme temperatures, the oxygen aggressively reacts with the carbon anodes, forming carbon dioxide. The sheer violence of this chemical reaction generates its own massive heat, meaning these cells are actually self-heating. But it also means those massive, incredibly expensive carbon electrodes literally burn away during the process and have to be continuously replaced. It's a violent, exhausting chemical loop for sure. And finally, part 5. Everyday aluminum applications. So, after surviving the caustic soda, the intense pressure, the extreme heat, and the massive electrical reduction, where does our little rock actually end up? Well, everywhere. The resulting aluminum and its various compounds are amazingly versatile. Just look at this list. It lands in everything from aluminum borohydride, used as an additive to jet fuel, to aluminum borate for specialized glass and ceramics, all the way to aluminum chlorohydride, which, is the active ingredient in the antiperspirant sitting in your bathroom right now. We even use aluminum fluorosilicate to create synthetic gemstones. It is completely woven into the fabric of our modern lives. So it leaves us with a kind of staggering and perhaps slightly sobering final thought. We interact with aluminum constantly, right? We drink out of it, we fly in it, we build our homes with it. But when you look at the extreme lengths we have to go just to pry it from the earth, the boiling caustic soda, the high-pressure vats, the hundreds of thousands of amps of electricity, and the continuously burning carbon electrodes, every single piece of aluminum we touch represents a massive, energy-intensive victory over nature's absolute strongest chemical bonds. Next time you hold an ordinary aluminum can, ask yourself, what is the true energy cost of this modern marvel? Thanks for joining me on this explainer, and keep questioning the science hidden right in front of you.